в путь.
I would like to introduce Artem Kotelskiy. He will talk about blockchains, future, present, and past.
Thank you very much, Vartan. Thank you for the invitation. It's an honor. Yeah, let me just introduce myself a little bit. I am a mathematician by training. I was, my research was in low-dimensional topology. I studied three manifolds, knot theory, symplectic geometry, things like this, for about 10 years. And yeah, and I had a kind of a hobby, a side hobby, where I was really interested in blockchains and how, what they are, how they enable new things, etc. And then over the years, I realized that really blockchains is another research area which encompasses many other fields. And this is actually what I love most about blockchains, that it's an intersection of computer science, economics, cryptography, and mathematics. And recently I also made a switch in my career, and I left the University of Stony Brook to be a researcher in a venture fund focused on blockchains. So that's a bit of background about me. I was born in Yerevan on the day of independence of Armenia, funnily enough. So yeah, I'm really glad to be here and speak to my passion and what I do. Okay, so let me start with a talk and maybe just one comment. I really want you to understand everything that I'm talking and just to get some value out of this talk. So if you have any questions, just stop me, like either raise a hand on Zoom or just speak out loud and let's discuss, because this is the best way. All right, so let me start. The plan for the talk is essentially in the title of the talk. I'm going to talk about the past, present, and future of blockchains. And the past is really kind of on the technical level, it's about how Bitcoin works, right? And I will talk about it. But before that, I will also cover cryptographic primitives, because that's what we will need. And maybe even more importantly, I'll cover why the fuzz, why kind of everyone is, well, not everyone, but people that are excited about blockchains. And there's really two perspectives on this. One is economics perspective, and there's a second one, which is a computer science perspective. After covering this, and this is going to be the majority of the talk, about one hour, I would say. And Artan told me that it's okay if I go 1 hour and a half. Please stop me wherever you think, I'm getting too long or something like that. But after the past, I'll cover present in the blockchains. And the present really is focused on Ethereum. It's a new blockchain, and the concept of smart contracts. So I'll explain what that is and why it's exciting. And then I'll talk a little bit about the future, or kind of where the current research areas are and what are the challenges in front of blockchains. And this really, the major two challenges are the scalability challenge and the privacy challenge. Okay, so let's dive right in. So let's start with the economics perspective, since it's probably the easiest one. So first, let me say that there's different ways to transmit value, and one of the really great ways is cash, because I have like a bill, and I can give it to someone, and that's it. That's the transmission of value. Very easy. Nobody has to know about it. It's really awesome. But there's a problem. It's not electronic. So I cannot send cash right away, for example, from New York, where I am based, to Yerevan. I would like to be able, but I cannot. I need to pay fees. I need to register, blah, blah, blah. All that stuff. So what can we do? So now let me kind of explain the solution that our world came up with. Is the main entity behind the solution is a bank, right? So bank has a database, and in that database they kind of they know all the balances of people. And instead of, for example, I hear, right, Alice and Bob, instead of Alice just giving a bill of $100 to Bob, Alice instead tells bank, hey, subtract from my balance 100 and add to Bob's balance 100. And that's a transmission of value nowadays using banks. And by the way, banks never do anything when you do this in a bank transfer. They just, they just kind of really just change the database. And they kind of once in a week or once in a month, they settle all the differences that they have if they need to. So it really does work like this, except when you need to send overseas, it's much more complicated. So let's talk about the major problems with this design, and that's really the driving force behind blockchain. It is why blockchains came about. So the first one is the incentives. Basically, the system is not incentive compatible, and the reason is because the controller, the bank, has too much power. So first of all, it has the power of keeping the ledger, who has which balance. Second, which is even worse, we actually give them our money. So it's not only they maintain the database, they actually have our cash. So they have immense power, and with that power, their incentives are distorted. They're not incentivized to serve the public, so to speak, because they have just too much power. And I mean, this manifests itself in various ways in the real world. I would say kind of the bailouts in 2008 are probably the most famous and egregious examples. There's also excessive money printing that is happening kind of recently, but there's many others. And the second, which is kind of less severe design flaw, but still is an important one, is that it is very centralized, right? The bank is one entity, and so it is subject to a central points, subject to a failure at that point. So, there could be data breaches, there could be hacks, et cetera, and we've seen many of those. So that's kind of the backdrop for why introduce a blockchain. So now let me talk about the design of blockchains. The key thing that happens is that the bank, the entity that maintains the database, is decentralized into a peer-to-peer gossip network. And we call different entities in that network nodes. So that would be node 1, node 2, node 3, node 4. And they all maintain the same database, okay? And kind of the punchline is that it works just as a bank. Alice sends to that network a message, hey, subtract $100 from me, add $100 to Bob, and the network does that. And there's two very important caveats. Alice doesn't give cash to this decentralized network of blockchain. So, it doesn't even know about dollars. It has its own native currency, okay? In Bitcoin, it is Bitcoin. In Ethereum, it is Ether. In other blockchains, it's something else. So that's the first key property, that Alice doesn't give any kind of extra power to this network. And then the second is, well, it's no more central, right? It's not any more centralized because it is distributed into many nodes. And so there's no one entity that can leverage its power over the database. There's tons of questions how this works, how, for example, why node cannot do what Alice did, just subtract balance, etc. And I'll talk to that. It's basically because Alice has to sign the transaction, okay? So that's the economics perspective on a blockchain. Now, next, I want to cover computer science perspective. What blockchains really are from the computer science perspective. But before that, are there any questions? Okay, yeah, great. So let me continue. So from the computer science perspective, it's a little bit different. So in computer science, there's a very famous problem called state machine replication problem. And the problem is kind of easily stated. It says, there's a bunch of nodes that are trying to stay in sync. And think about this as a databases for some kind of service, like, I don't know, for example, you can think of Google's databases. Google has database 1, database 2, database 3, database 4, and it has 4 of them.
Can I ask you a question?
Yes.
Am I right that there is no some kind of a private information, so all people can see all kind of information about other people?
That's right. Except, the identifiers on the network are not names. It's like a address. It's like a 256-bit address. So it's kind of pseudonymous. If I have an address on Bitcoin, nobody knows that it is my address. But if someone wants to if someone tries to figure out whose addresses are these addresses and etc., then yes, it becomes public. So this is what we call it pseudonymous. It's public because everybody can see all the transactions, but the addresses don't contain names. So, and I'll speak to that at the end of my presentation. But you were right, Marhan. Yes.
So all people, they have some kind of usernames, and I can see that these user all information about this person, but I don't know who actually this person is. Yes.
Yes. And a username is, you cannot even choose it. It's really just like a string of letters. Yeah. Okay, so let me continue. Thank you for the question. Please do ask any questions. Yeah. So now let me continue. So basically, these nodes are just different databases that are trying to stay in sync. You may ask, well, why can't Google just use one database? Well, it's because they want a backup, right? What if their database just goes off, or electricity is lost? So Google usually prefers to have 3 to 4 replicated databases. That's why it's called state machine replication problem. They want to replicate the database. So they have these 4 databases. And if you think about what they want is, well, they want to accept transactions from clients, and clients could be just users which do search requests, but they want to do it in such a way that they're all in sync, right? So if client 1 sends a transaction node 3, all other nodes, they also want to have that transaction. So the goal really is a protocol, and a protocol is an event-driven code. So, if I receive a transaction, do A, B, C. So it's an event-driven code to be run by nodes, satisfying 2 properties. So the first one is consistency. And this is a key property that all nodes agree on their histories. It really they have to replicate themselves, okay, to be good backups. And then the second property is liveness, meaning that every submitted transaction has to be eventually added to node's history. Otherwise, well, the system doesn't work, right? If you cannot add transaction. So this is the computer science perspective, and this is kind of the most academically widely known perspective on a blockchain. Now, let me tell you, well, what's the connection with blockchains? Well, here it is. And in order to explain this, I need to talk first about parameters and assumptions, okay? So the first parameter, very important one, is the latency. What's a message delay, maximum message delay in this network? So if client 1 sends some transaction, after how many seconds nodes hear it? Or if node 3 heard a transaction, it wants to broadcast it to node 1, node 2, node 4, how many seconds does it need? So the latency is important. The second one is whether or not the setting is permissioned. And this is probably the most important one. If you are Google and you just have 4 databases, this is the permission setting, because everybody knows, including nodes, that there is a set of nodes, it's 4 nodes, and they're trying to set it to stay in sync. Okay? And then the third one is dishonest nodes fraction. So how many nodes in the network are buggy or malicious? So for example, in this case, could be that node 2, electricity went off, so it doesn't work. Only 3 nodes work. So the fraction would be 1/4, right? So that's an important kind of parameter. And let me say that this problem, and the problem is to come up with a protocol which satisfies consistency and liveness in the permission setting. So in the setting where all the nodes are known, is actually well studied and solved. And in particular, if the fraction of buggy or malicious nodes is less than 1/3, there exists such a protocol under certain assumptions. And there's this work of Dole Strong, kind of which solves it under how to say it, under any assumptions, but the solution is not efficient. And then there's kind of the most famous paper of Dwork, Lynch, and Stockmeyer, where they solved this problem in the so-called partially synchronous model. And their key assumption is that the fraction of faulty nodes is less than 1/3. Okay. And so here's the punchline. Okay. But now you realize, okay, this is very similar to blockchains. In blockchains also we have nodes and we have clients, which are users, which send transactions. But the key difference in blockchains is that we don't want anyone to control the network, right? Because that's what I told you in the economics perspective. The whole point of a blockchain is that nobody controls the network, and the nodes can either add themselves or exclude themselves. The network is permissionless, okay? So that's kind of the punchline. Can we solve this state machine replication problem in the permissionless setting, where everybody can join a network if they want, the network nodes, okay? So that's kind of the academic viewpoint on a blockchain. And this was kind of an open problem up until 2008. And in 2008, Satoshi Nakamoto solved this problem. How to solve this consensus problem. Sometimes people say, people talk about this as a consensus problem, how nodes can come up, can talk to each other and come up with a consensus history. So can we solve it in a permissionless setting where anyone can add nodes to the network? Okay, any questions? Okay, let me.
I have a question. So
sure.
You are saying that that there is no some kind of a private information, but okay, we have computers where such that they keep all these private and all this information. So in the same way as you said in the beginning, I can hack these computers and get some kind of a private information, usernames, and so on. So why this is different from what we already have? So that's probably a stupid question.
Yeah, well, great question. So let me talk to this point. So if you have a bank and you have usernames and balances and etc., the hack is a problem not because it exposes information, although exposing information is a problem. Don't get me wrong, but the key problem is that the hacker can just transfer balances to themselves. Okay. Whereas in this particular model, even if they break the node A, the node 2, let's say, right? The majority of other nodes, node 1, node 3, and node 4, are not broken. So even if node 2 happens to be a faulty node or a hacked node and says, hey, client 2 just transferred $10,000 to client 3, where client 3 happens to be the hacker, right? That's what the strategy of a hacker would be, right? The hacker could be client 3, and they could break node 2 and say, client 2 transferred $10,000. But the network will reject that. The reason is because the majority of the network, node 1, node 4, and node 3, are honest nodes, and they are trying to stay in sync. Okay, so the key idea here is to trust the majority of the nodes for the history, and that way nobody can change anything. As long as, I mean, if the hacker hacks all four nodes, we're in trouble. You are right. But for example, in Ethereum, there's 500,000 nodes. So hacking even 1/3 of 500,000 nodes is just infeasible. It will not happen. Does it make sense?
Yes, thank you.
Sure, yeah.
So at least if I want to steal some money, then I need to hack like more than 250,000 nodes.
Exactly. Okay. You need to hack the majority of nodes. That's right.
Okay.
Which is very unlikely to happen. So yeah, that's the resiliency of this network.
But is it still possible? Like, do people cheat in some way still, or do you know?
Is it possible? Say it again.
Is it possible, like, to cheat or steal some money still in some kind of a way?
I mean,
of course, you can't hack so many nodes.
Yeah, the network. You know, you're asking a question which opens the door to like an infinite research papers, and the answer is it's not obvious. I mean, the system is built in such a way that you cannot, break it. That's why blockchains exist. That's why Bitcoin exists. That's why Ethereum exists. But of course, there's subtleties. There's subtleties in assumptions. There's subtleties. There's many subtleties. But I cannot talk about them until I cover the system. So let me maybe go into the system now.
Can I ask one more question?
So, sure. Yes.
Am I right that you have like users, and they all have this kind of all users, they can see all the information, like what's happening just around, that you send some amount of money or just another person send some amount of money. And what hacker can do, he can hack some information of one user and change information saying like, okay, this person sent money to this person. But the system is going to decline that because other users they don't have this information. So something to be approved, all users, they should have the information that this person sent money to this person. Am I right?
Yeah. Yes, or almost. I mean, so first of all, when you say users, you really want to say nodes, okay? Node. So that's the first thing. So there's two parties. There's users, which are clients. They just send transactions. But then there's nodes which maintain the network, okay? And what you said is true about the nodes. If you want to change something in the network, you really need to control the majority of nodes in the network. You are right, yes.
So this is some kind of a democracy. So like something is true if the majority of nodes, if it's written in the majority of nodes.
That's right. Yes, exactly. And I'll talk a lot more about it. But that's the key idea: is that the majority of nodes have to agree on something. But there's other layers of defense. And for example, one cannot just go there and say client 1 sent some money to client 2. Just because It is because client one has to sign a transaction. Okay, so this is a second layer of defense, which is a cryptography. So let me now start with the cryptography a little bit, because that's kind of important in this context. So this was just an overview of what's going on. Now we're kind of diving one level deeper into how Bitcoin works. So I need to step back and start with cryptography. Any other questions, maybe? Perfect. So let's go for it. So there's two cryptographic primitives, and the first, in order to explain how Bitcoin works, there's two cryptographic primitives. The first is digital signature. So a digital signature scheme really consists of three functions. There's a generation function, which generates a private key and a public key. And by the way, public key is the same thing. Maybe I'll even draw a little bit. So this is the same as address of Alice. Okay, so this is kind of the username, actually, let me precisely say, in the blockchain world, this is a username. Okay, so if you want to go to Bitcoin and use it, what you really do is you just run this function gen, and it generates you your username, which is public key, and then it generates a private key. Now, what does private key do? What does a private key do? Well, with private key, you can sign any message, okay? And if Alice wants to send $100 to Bob, what Alice does, it takes its private key and it signs this transaction, 100. I want to send $100 to Bob. And when they sign, it gets a signature. It's an electronic signature. So it's kind of like in the real world, but it's an electronic signature. And by the way, it's not one signature. It depends on the message, you see? In the real world, your signature is the same for any document, right? In the electronic world, the signature depends on the message. Message is a parameter. And the third, the key function, is the following, that one can run a function verify where the parameters are public key, so the username of Alice, message that Alice sent, and a signature that Alice outcoded. And basically, it verifies if Alice signed the message. So it's true if Alice did sign the message, and it false otherwise. So it's kind of a very clever way of signing things. And there's a whole field of cryptography which has to do with how this works. I will not go into it, but yeah, it's really wonderful that we can have it. And so just to reiterate, Alice, which has its username, public key, and a private key, it sends a message. Let's say it can send a message to a Bob or anything else. And the message contains public key, message, and signature, right? And then Bob can check if Alice signed the message by running this verify function. Now, here's the key point. Alice didn't send its private key, right? So Alice maintains its private key in a secret, but it can sign messages and send to Bob, and Bob knows, hey, it's Alice who sent it. So it's a way to authenticate messages. So for example, if I publish my public key on my Twitter, later on, I can always send messages on my Twitter signed with my private key, and everybody will know it's me because I published my public key. Okay, so it's kind of a way to convince everyone that it's me who is sending the message. And the key thing, of course, is that you want this scheme, this digital signature scheme, to be unforgeable. So nobody else can generate signatures if they don't have private key. Otherwise, it's useless. I mean, you know, if Vartan could generate the same kind of signature as Alice, there's no value in private key of Alice. So it has to be unforgeable. These signatures, such that the verify is true, can be only produced by those people who have private key. Okay, and this kind of gives you a hint for, you know, if we run a little bit back, for example, in this slide where Alice sent transactions to a network of nodes. Now we will require Alice to sign these transactions, and only signed transactions, correctly signed transactions, will be accepted by a network. So the network will need to run the verify function, and if the signature is invalid, the transaction goes to trash. So this is why Vartan, this is a kind of a second answer to your question. Why nobody can steal money from Alice? It is because Alice has a private key, has its private key, and nobody else controls private key of Alice. So if you are in a block, if you're in Bitcoin, you have your private key. If you don't lose it, nobody will steal your money, because nobody will be able to sign a transaction on your behalf. Does it make sense?
Yeah, so you said that you are not allowed to choose your public key. So it's some kind of your username, your name.
Yes.
And are you allowed to choose your private key, or it's
no? It's a pair that comes out of a generation function. But the generation function, you might say, well, so the generation function, you can feed it anything. Like you can feed Artem, like a name Artem or a name Vartan. So a generation function just takes as an input some random string, and it outputs a private key and public key.
But what's the difference with the password? So when I just log into my bank account, I have a username and password. Is it the same, or it is different?
Yeah, it's a great question, right? So in a way, like the concept is very similar, right? Indeed, you know, you have your private key, which is a password, and you can access your bank account with your private key, which is a password, and then, you know, send messages. So you're absolutely right. It's the same concept, except when you do it with Bank, what Bank does is they receive your password, and then they go to their database and they check, this user has this password. So it's all manual. It's just based on the database, right? But here it's a cryptography. So in the case of banks, the database can be hacked and your old passwords are compromised. In fact, this is only one problem. There's many problems with password username model. Whereas here, it's on the mathematical level. If you don't have private key, you will never access this account, this username public key. If you have a private key, you will access this. And there's no way around it. It doesn't matter. And or maybe I should say the key difference is that the person has to hack you. You control the private key and nobody else. So in the case of banks store your password. Here, nobody stores your password. That's the difference.
Right, so you kind of keep the information about yourself. There is no database keeping all your passwords, usernames.
Yeah, okay. That's right. Yeah. This is what if you
forget your private key or just lose access to that?
Great question. So there's a very important word. It's called self-custody, and this is what I'm talking about. Is when you control your private key and nobody else. This is kind of why blockchain are what they are, is because it's the only system where only you control your kind of digital balance. to answer your question, unfortunately, yes, it comes with drawbacks. If you lose your private key, you lose your account and you lose your money on that account. And that's actually one of the major obstacles for user adoption, for why most people don't use Bitcoin or blockchain. It's because it's very easy to lose private key. And there's solutions. There's a whole kind of field which is called account abstraction, which talks about what we can do about it, and et cetera, et cetera. But let me not go into that. But to answer your question, unfortunately, yes, you lose your access.
And what is a private key? Just a sequence of numbers, letters?
Yes. Yes, it's just a string.
Is it huge or short?
No, it's short. It's short. Yeah. It's you store it in a file essentially.
I mean short. You mean like 10 letters?
It's like 256 bits.
Ah, okay.
Or
okay.
Something like
it's huge. For me, it's huge.
Yeah. I mean, it depends on what big and small is. It's huge in the sense that nobody will have two same private keys, because the generation function, it's cryptography. The way this works is super beautiful. It uses groups and exponentiations and groups and et cetera, et cetera. I'm not talking about it because it will take another 2 lectures to explain how this works. It's beautiful stuff. Maybe for those who are interested, you can Google RSA. This is kind of the quickest way to understand how this works. But yeah, once you set up the system, it's a 256 long string, and it's never the same. If you generate something and I generate something, it's never going to be the same. Okay. All right. So let's go further then, or maybe are there any other questions? Okay, let's cover the next cryptographic primitive. Let me check how I'm doing on time. Okay, hash function. Okay, what is a hash function? So this one is interesting because it's not a signature, it's just a function, okay? And it takes as an input any length message. I mean, to be completely honest with you, it takes in not any length message, but like anything less than 2 to the power 256. So it's very, like, the largest string it can take is super large. You don't have to think about it. You can just think any length message. And the output is 256-bit number. So this has length 256 of zeros and ones. Okay. And in cryptography, a hash function is a hash function when it has the following key properties. So the first one is irreversibility. So if I give you that hash of something is something, you will not be able, if I just give you 256-bit number, you will not be able to reverse the hash function, find a message whose hash is this number. So the inverse function is not computable. The second is collision resistance. This one is confusing because, you all are mathematicians, so you'll quickly realize if we're mapping any length message space into 256 length message space, there's going to be a ton of collisions, right? There's going to be a ton of, f of x equals f of y. So you might say, well, it cannot be collision resistant. But what I'm saying is it's cryptographically, practically collision resistant. So if I ask you to find x and x prime, you will not be able to find it. It's counterintuitive, but it is what it is. There are such functions where we know theoretically there is a ton of collisions, but we are not able to find them. In fact, you can kind of estimate how much time you need for that, and it's on the order of, I don't know, tens of millions of years or something like that. So it's just infeasible to do it, even if you have supercomputers. Except if you have a quantum computer. If you have a quantum computer, finding collision becomes possible. So we need to be careful here. So all cryptographic concepts I'm talking about, it's pre-quantum computing, okay? Yes, do they might have a question? Okay, so the third is uniform randomness. This one is a little trickier. Basically, this function just looks like random. It looks like it's a random function. Okay, so if you cannot even control it from the input. So if my input is just a number, let's say number 12, 1, 2, it gives some output. If I just change one bit and say one symbol, let's say the input is now 1 instead of 1, 2, it's 1, 3. The output is completely different. So it's a completely random function, and each output basically has this roughly the same probability as every other output. There's mathematically rigorous way of saying it, but I don't want to do that because it takes time and it's not super helpful. Just think about it as a random function. And so now you might ask me, well, why do we need it? The use case is what's called a proof of work. So Bob could send a message to Alice in message 1, and then Alice could send a message 2 to Bob, such that the hash of message 1 plus message 2, and remember, hash is just a number, right? It's a number. So suppose Alice sends a message, sends such a message to that hash of the concatenation of these two messages is less than a certain number n. Okay, and let us suppose that
can I ask you a stupid question?
Yes.
What is a message?
Message is just a string.
Just what?
It's a string. It's a sequence of symbols.
So so on the left hand side, when you just sign private key in the message, it's the same message what you have on the right hand side.
Yes, that's right. When I say message, is just it's just a bunch of symbols. I mean, for example, my name is Artem is a message, or I don't know, Bartan is a message. It's like any string of symbols, essentially.
Oh, and this is some kind of also part of your password. So the private key in the message is also
private key. You can think about it as a message. Public key, you can think of that as a message. But the point is that when I say message, it's something that one entity sends to the other entity. For example, I don't call private key a message, even though private key is also just a bunch of symbols, right? The reason is because Alice never sends private key to anyone. So I don't want to call it a message. Does it make sense?
Yes, but why do you need to send a message to someone?
Great question. Well, if I want to send you, let's say I want to send you 1 Bitcoin, I need to send a message to Bitcoin network that Artem is sending 1 Bitcoin to Vartan. I need to first sign this message and then to send this message to this network. Otherwise, how network can know, how nodes in the network will know that I'm sending Bitcoin to you?
Do you really write words that I'm sending 1 Bitcoin to?
No, I mean, now you're asking about kind of the details. There's a certain language in Bitcoin network, like I will write my username, your username, and then some symbol between them, and then 1 Bitcoin, something like that. There's a particular language in the network, and it is predefined. But you can think about it as just simple words. Yeah.
And this message is going to be put into nodes. Am I right? So all these 500,000 nodes is going to be written in all these nodes.
Exactly. Yes.
Okay. So this is something you send to all people, saying that we can send this money.
Yeah, a message in my network, message is sent to all the people, and this these are just examples that I'm using to kind of illustrate you cryptographic primitives, but we're yet to come to the punchline of how the whole system works. So yeah. But let me put.
Oh yeah.
Yeah. Okay. Let me just finish this slide, and then I'll pause for questions. So the proof of work is that basically Alice finds such a message that the hash is less than a certain number. Now remember, hash is a random function. So if I ask you to find a hash that is less than 32, it's going to be very hard for you, right? Because a random number from 1 to 2 to the power 256 is going to be more than 32. You know, there's 32 numbers before 32, and there's a ton afterwards. So you're gonna try many times to figure out a message 2 such that its hash is less than a certain number. So this is what's called a proof of work. So if I happen to send Vartan a message whose hash is less than 32, Vartan knows that I must be gone crazy. I tried many numbers or many messages in order to find such a magical message that its hash is less than 32. Why do you know this? Well, it's because a hash is from 1 to 2 to the power 256, and 32 is a very small number in this range. Does this make sense?
But if all, just maybe I misunderstand something. If all people can see my messages in the nodes, why do I want to code them? What's the reason to code these messages?
You said code?
Yes, I mean why do I need this hash function?
Yeah, the hash. Great question. You're running ahead. You're running ahead. Now let me explain you the whole system. Okay. So now let me explain the whole system, and hopefully everything will be in place.
And sorry, there is also a question in the chat. If you can take a look.
Yes, it's a proof of what type of work. It's the work. The proof of the work is basically going through different messages. Sorry, the work is running through different messages. Message 2 could be 1, 2, 3, or some other string. So you have to you iterate through many message 2s, and that's the work that you've done. It's basically it's a case-by-case analysis. You know, case 1 doesn't work, case 2 doesn't work, and then you do many ways, and then some of that works. So that's the type of work that is going on. Yeah. Thank you.
May I ask one more question? So
sure.
You have this hash function and you described its properties. How do you quantify them somehow? I mean the following: I come up with some hash function, another person comes up with a different hash function. How do you decide that one is better, one is more random, one is more irreversible? Is this somehow like a rough understanding, or is this mathematically quantified? How do you determine which one is better?
Yeah, it's a great question. So first of all, yes, I mean, let me say that this is a field of applied cryptography. So this hash function is really just a deterministic function which involves XORs and some if I remember correctly, yeah, I forgot the precise word they use it. Yeah, but you know, you can run it even with your hands, but you know, it's really a function that you write in your computer. So that's the first thing. So it's not like a theoretical function, it's a practical function. Now, to answer your second question, how do people realize which function is good, which function is not, right? So indeed, there's tests, right? There's tests for all 3 of these properties. And there's tests that, you know, different laborers came up with. There's Wikipedia pages about it, about those tests and et cetera, et cetera. But those are all, let me say, empirical. So unfortunately, there's no theorem that says, hey, this hash function is uniform random for sure up to this, I don't know,
level of precision.
Exactly. Yeah. Unfortunately, there's no such theorem, and the reason why there's no such thing is because people kind of on purpose pick a very bizarre hash function. Like the way it works is just kind of,
it must be bizarre. It must be.
Yeah, exactly. Yeah, it shuffles your inputs, it sorts them, and then shuffles one more time, sorts them. So it's like a bizarre function which is extremely hard to analyze. So there's no theorems about it. All tests are empirical. Mm-hmm.
So, for example, this randomness is like, if you take small set of outputs, you get one notion of randomness. If you get large set, you get a different set. So it all depends on the problem, maybe, that you need some kind of, because all these randomness notions are different, and depending on how you quantify it, you end up with very different hash functions. So it's a problem-specific type of thing.
Yes, you are right. I mean, there's various ways to define randomness, although in applied cryptography, they kind of converged on one particular definition. And I can fetch it after the talk and send you. It's a little bit of annoying definition, to be honest. That's why I prefer. That's why my mind just kind of forgot it. And like for me, it's just useful to think about uniform randomness. Yeah.
Thank you.
But thank you. Thanks for the questions. I have one more in the chat. Is the hash function also part of a message? Because otherwise, how would the other members of the network could verify my message? And my worry is that all this message passing becomes exponentially complex. Okay, these are great questions. Let me explain now the system, right? Because so far, I only told you the big picture, the motivation, and then I told you kind of the main idea, decentralize the network. I told you this cryptographic primitives, but I didn't actually tell you how the system works. So all this was a build-up towards how the system works. So Yanis, let me tell you how the system works, and then maybe you'll have more precise questions after that. Okay, so here's how it goes. So first of all, we need to understand that the blockchain is simply a database, and it is a database of transactions, classically. So, but it has a particular data structure, and the data structure is a blockchain. So what does this mean? It means that there are blocks. So for example, apologies. There are blocks, right? And the block, this is block n, this is the next block, block n plus 1, this is the next block n plus 2. Each block has a bunch of transactions. So it's a sequential data structure. Now, how these blocks are connected? Well, hash, so block n plus 1 contains a hash of block n, of the previous block. Okay, so that's why the blockchain is a chain of blocks, because it's a bunch of blocks connected by hashes. So this particular field is a number, 256-bit number, which is a hash of this block. So you know that this block is the next, is the block that is next after that. So that's the data structure that is being maintained. You might ask, well, why so complicated? Why not just a database? Let me explain why, because there's good reasons for that. Okay, so now let me kind of walk you through a transaction life cycle. So let's say Alice has 3 Bitcoins and Bob has 0. And let's say Alice wants to send 3 Bitcoins to Bob. Now, you might ask, well, what exactly Alice and Bob are in the network of Bitcoin? Well, Alice is Alice's private key and Alice's public key. And remember, public key is the username. Bob has its own private key and its own public key. Public key is the username of Bob. Alice knows public key of Bob. Bob knows public key of Alice. But the private keys are, of course, secret. The first step is always broadcasting a transaction. So Alice, let's say, broadcasts let's say it's transaction 10, right? Number 10. So let's say it had 9 transactions before, and it broadcasts its 10th transaction, and it says, send 1 BTC to Bob. But it doesn't say Bob, because the network doesn't know about names. The network knows about usernames. So it says to public key of Bob. Okay, so that's the transaction. Now, next, Alice also sends a signature, right? So it generates a signature using private key. And this signature is the way nodes will know that actually it is Alice who sent the transaction. Okay, this is what prevents me, Artem, from sending Alice's Bitcoins to Bob. If I send such a transaction, I will not be able to include this signature of Alice. Okay, so that's why it's a self-custodial system. That's why nobody can do transactions on Alice's behalf. Okay, so that's the first step. Any questions?
Why is it not possible to hack Alice's signature? I mean, just as a string. How do I know who produced that string since I don't know how Alice produced it?
Yeah, so you are right. I mean, the point is that you assume that people say, people don't lose their private key. So as long as Alice doesn't lose private key, we know it is Alice. To answer directly your question, we don't know for sure. It is a hacker who hacked Alice's computer and got Alice's private key. So, but notice that a hacker needs to hack Alice's computer, not a bank. So it's not single point of failure system. In order to hijack the system, you need to hack someone's computer, and you need to know that you want to hack someone's computer. And you don't even know maybe how many Bitcoins Alice have. You don't even know, like, is it worth hacking their computer or not? But you're right, hacker, this system is, just as any other electronic system, to be honest, is prone to hacking. Now, let me say that there is solutions to that. This is called multi-sig wallets, where you require not only signature of Alice, but signature of Alice's friends as well. So you identify one of the key problems in the user interface of Bitcoins with your question. But let me say that there are other solutions to that, which I'm not going to talk about, unfortunately. Yes. Someone else had another question? No? All right. Let me proceed then. So here's the second step, which is basically collecting. So first of all, the way system works is that this decentralized network of nodes runs by picking a leader each step, okay? And at each step, there's a chosen leader. Let us suppose that it is node 4, and then this leader does the following. It collects a bunch of transactions, okay? And, Alice sent one, maybe I sent another, Vartan sent another. So it collects all of them, all right? And then it is a very important step. It checks the balances and signatures. So what does this mean? The node 4 checks whether or not Alice's signature was valid. So it runs the verify function. So we know for sure that it was Alice who sent the transaction. So this is what I mean by checking signatures. Well, how about checking balances? Well, it checks, for example, Alice wanted to send 1 BTC. Does balance of Alice has 1 BTC? Because if Alice has only half of Bitcoin, it cannot send 1 BTC. So the leader checks whether everyone has enough balances for transactions. Okay. And by the way, I forgot to say, Alice also sends a fee. And you might ask, well, why Alice needs to send a fee? I'll talk about fees a little bit later. But Alice also sends a fee, 0.1 Bitcoin or some other fee. Okay, so that's one thing that Node 4 does. It validates transactions. This is very important because if you don't validate the transaction, the system just doesn't work. So that's what Node 4 does. Now next, Node 4 does one of the most important things. It mines a new block. And this is, by the way, how it becomes a leader. So a leader in the network is the node who mined the block. This is now now here's the question: how does a node mine a block? And this is how it goes. It finds a number k such that the hash of k plus previous block is less than a certain number n, which is a difficulty parameter. Okay, so you might ask me, well, why can't everyone mine a block? Well, it's because this number n is so small. It's like, I don't know, it's not 32. 32 is very small, but it's like, it's fairly small. I don't know, it's 2 to the power, I don't know, 200. And so the difficulty of finding such k, you need to go through many numbers. You go through number 1, you go through number 2, number 3, number 4. You need to go through many k's before you find such a k that the hash of k plus previous block is actually less than n. And that's what it means to mine a block. And it's kind of similar to how you mine gold, because you need to dig before you mine gold, right? So it's kind of same concept here. You need to hash with the number 1, hash with the number 2, hash with the number 3, hash with the number 4. You do case by case until you get your mining. You mine a block. You find such a number k, that hash of this number plus previous block. And by saying previous block, I just mean a message that contain, or a string that contains the previous block is less than a certain number. And that's what constitutes a mining a block, right? So this new block, n plus 3, by the way, this has to be hash of block n plus 2. This is a mistake, I'm sorry. So the new block requires validity of balances. So, nobody gets to have a negative balance. By the way, in banking, this is not true. People are allowed to have negative balances. In Bitcoin, there's no way to have negative balances. Second, everyone has to have valid signatures. So everyone needs to know that it is Alice who sent the transaction. And finally, the block has to be mined, right? So the hash, this hash of k plus previous block, has to be less than a certain number n, which is hard to find, as we discussed. So this is, Vartan, your very valid question on the previous slide. You asked, why the heck do we need hash functions in all this system, right? And that's the answer. That we need hash functions in order to elect leaders. And we elect a leader in the round by saying that, by basically this leader, node 4, giving us a number k, which they were able to find such that the hash is very small. Okay.
The number n and the hash function are universal, like, or should they be indexed?
No, they are universal. Yeah. Sorry. Hash function is universal. In Bitcoin, it's called hash 256. You can Google it, and there's a Wikipedia page about it. It's a particular function. Now, the number n is what makes things very interesting, because you want your blocks to appear once every 10 minutes. Okay, you don't want blocks to go every minute or every 10 seconds in Bitcoin. You really want once per 10 minutes. But the point is that if there's many miners trying to mine a block, if there's many GPUs and ASICs trying to find such a number k, there will be faster block times, right? There will be faster. So this number n, basically every week, is adjusted in such a way that the blocks appear every 10 minutes. So the number n is adjusted by a network every week, if I remember correctly. I'm not 100% positive. Okay, so yeah, absolutely. This slide kind of explains how actually the Bitcoin network works. This one is a super important one. So if there are any questions about this slide, please go ahead.
And the algorithm that updates the end, you say it's a network, but there is a code behind it, right? Is that who has access to that? Who controls that? Is there some supervising entity?
Yeah. So yeah, I'm glad you asked this. Yes, there's a code, and this is a code that every node in this network runs. So there is a particular code. It's called Bitcoin Core. There's a GitHub page where you can download this code that every honest node has to run, and basically anyone has access to this node. And the point is that we assume that the majority of nodes are honest and they run precisely that code. And you might ask, well, what if node 1 runs a different code? And I'll get to that on a second slide. On a second slide, I'll explain why this network is resilient. Let me also say that, after a leader, who mines the block, what they actually get the fee that Alice pays. So they're incentivized to do it first because they're incentivized to include Alice's transaction because Alice adds a fee, but they're also incentivized to go over all these hashes to burn all so much electricity in their GPU farm or ASIC, whatever, because after this, they get what's called a mining reward. So it's an issuance of BTC. So the network issues new Bitcoins every block to the miner who mined that block. And that's this is the incentive layer of the system. Why do people care about it? Why would nodes run this, right? It is because of this mining reward that they get when they mine a block. That's the incentive that they have. So this system is both cryptography, it has cryptography because we talk about digital signatures and hash functions. It also has this economics layer where you set up certain mining rewards, fees, and etc. So everything has to come into the right place in order for this to work. Okay, so let me maybe go further and explain you why the system makes sense and resilient. And essentially, the way the nodes kind of all stay in sync, they stay in consensus, is the second idea of Satoshi Nakamoto. And the idea is simply the following, that, in the network, everyone, has a bunch of blocks, but they always have kind of a choice to build on top of which block. Maybe they can build on top of this block or this block or this block. And the rule that honest nodes follow is that they always build on top of the longest chain. So even though some dishonest nodes may build on top of some other blocks, like on the sides, the point is that the all honest nodes will build on top of the longest chain. And that's the second idea of Satoshi Nakamoto. Satoshi Nakamoto came up with two ideas. The first was how to use proof of work to mine a block, to elect a leader. And then the second idea is to say that actually valid transactions are those which are in the longest chain of the network. Okay, and this is what prevents the technical term, the so-called double spend attack. And let me not go into precisely what the double spend attack is. It's a certain attack that you can do on the network, but the point is that as long as 51%, the majority of the hash power, the majority of nodes power is honest, so it's not the majority of nodes, but rather the majority of hash power. So if you sum up nodes with the weights, where weight of a node is the power, the GPU power with which it kind of searches for hashes. So as long as majority of hash power is honest, malicious chains will not be able to outpace the longest chain. The longest chain will prevail. And so all nodes are incentivized to build on the longest chain. And so there's not even an incentive to try to hack the system. It's just impossible if the majority of the hash power is honest. And it is an assumption in a Bitcoin network that the majority of the hash power is honest. It is an assumption. So if most of hash power becomes dishonest, the Bitcoin breaks. But there are, by the way, things, scenarios to mitigate that as well. But just the system, as I described to you, really assumes 51% or more than 51% of hash power honest. And let me say that the key point that Satoshi came up with is that, you know, if you just come up with a system where nodes just vote, you know, I have a node, Vartan has a node, Alice has a node, Bob has a node, and we just vote, right? One node, one vote. This wouldn't work because everybody will just add many nodes and that's it. It's called a Sybil attack. But now, with this kind of proof of work idea, we translated our system from one node, one vote to a system where it's one CPU, one vote, right? It's my vote is as powerful as as the computational power that I provide to the network when I search to mine the blocks. And so this is kind of the key idea of Satoshi, is to kind of, you know, when you're in permissioned setting where you just have 4 nodes, it's okay to just vote and that's it. You can just vote. But if you're in permissionless setting where you don't know how many nodes there are, you really need to come up with some sort of proxy for how you vote things. And this idea of one CPU, one vote through proof of work is the ingenious idea of Satoshi Nakamoto. Questions?
So that longest chain, is it eponymous or anonymous, and is it publicized? Like,
it's publicized. Yeah, everything is public. Yeah, it's public between nodes, and if anyone wants to go and read it, it's public. Everything is public in this realm except private keys of Alice and Bob.
And if, let's say, somebody realizes that the longest chain is acting maliciously, now how does that get resolved? Like, what happens? Like, is there kind of like you know, kind of like a fail-safe mechanism? What do users do if they realize, or if some users are dissatisfied? Let's say.
Yeah, that's a good question. And honestly, I don't have a good answer to this. I mean, I think proof of work systems, and particular Bitcoin system, really does rely on this assumption. It's more than 51% of hash power is honest. Now, other systems like Ethereum and proof of stake systems have a way to defend against 51% attacks. But I don't think proof of work can defend, because if there's 51% of hash power which is malicious, even if we set up a new network with new nodes and new addresses and etc., well, they'll just come to this network and they'll mine our blocks. So I don't think this model has a particularly good defense scenarios against 51% attack.
And is it possible? Sorry, is it possible for somebody, let's say, to hoard like the system or the fees? Is there any way to democratize that in order to maximize buy-in and stakeholder engagement from a maximal number of participants? Is there?
Yeah. So this is a great question. This is what I was trying to convey. What you're describing is a Sybil attack. So I can spin up many nodes and kind of bump my weight in the voting in the voting round, right? But notice that this is not possible in this system, and this is the invention of Satoshi Nakamoto. Like, why is it's not possible? It is because the leader is elected according to the according to the hash that they found, and the probability with which they find this hash is proportional to the hash power that they have, to the computational power. So if you want to bump your weight in the network, you really need to contribute electricity. You really need to contribute GPUs and ASICs and whatever the way you do it. And so this is why it's very hard to hijack Bitcoin network. It is because for this, you actually has to, by the way, yeah, Bitcoin network right now, to hijack, you kind of need like you kind of need electricity on the order of a country. Like if you somehow own electricity of all, let's say, Argentina or Austria somehow, right? And you direct all that electricity power into Bitcoin, then you might be able to hijack it. But it's just too much electricity to be contained in one set of malicious hands. Yeah, so thank you for the questions. Those were great. Other ones? Are there any other ones?
You said that there are 500,000 nodes. Why do we need so many nodes? Why not just 500?
Yeah, it's a good question. I mean, when I told you this, I was talking about a different blockchain, Ethereum. So, and the answer there is a little different. So in Bitcoin, there's less nodes. In fact, it doesn't matter how many nodes are there in Bitcoin. It matters what is the hash power distribution between those nodes. Okay. So maybe let me proceed a little bit because I did want to talk a little bit about what's happening right now in the present and in the future. Maybe I don't get to the future part, but at least I'll cover the present part, because Bitcoin is great, but I would compare Bitcoin to, it's like it's a watershed moment. It's when people realize, hey, we can do such stuff. But if the really interesting stuff happens not on Bitcoin, but on new networks where people kind of realized, tweaked things and realized what exactly we can use this for other than money. Because Bitcoin is just money, just transmitting Bitcoins to each other. What else can we do with blockchains? Yeah, any question? No? Okay. And the answer is that, well, we can actually do any state transitions, because in Bitcoin, we have balances of people, and then we just, it's a one state. Now there's another state, and then transactions in between. Well, you can use any other state, right? You can like think about Turing machine, right? Alan Turing came up with, right? It has a state and it has transitions, and you can replicate it on a blockchain. And so this is what this next blockchain, Ethereum, came up. This was the paradigm change in 2014. And essentially, the idea is, well, but how exactly do we implement this? Because in Bitcoin, it's very clear. It's balances and the balance changes. That's it. But how exactly do we implement arbitrary state transitions? Like, what is, like, we need to include something, right? At least some rules. And here's an interesting idea. And the answer is what's called a smart contract. And this is a concept which is due to Nick Szabo, the prominent researcher in the space, and Vitalik Buterin. Vitalik Buterin is a young person, scientist, who came up with the Ethereum idea. Okay, so what are smart contracts? Well, the point is that there's two types of contracts on Ethereum. There's a regular account, which is controlled by private key. This is what I kind of explained to you. And essentially, it has a public address, a username, which is its public key. It has a private key, and it has a balance, right? This is what we're familiar with. But a smart contract account is a different thing. It's controlled by code. So this is this kind of very new idea that came into blockchain space in 2014. What if we can have accounts that are not controlled by humans, but that are controlled by code? What do they have? Well, they still have public address, but they don't have a private key. There's no private key. Nobody controls it. Instead, it has a code and it has a storage, and it also has a balance. You might ask me, well, okay, cool. What's interesting about it? Let me try to convince you in the remaining 3 minutes why this is interesting. So I always give, as an example, a splitting smart contract. So let's say Alice happens to have 2 ETH. By the way, Ethereum is a different blockchain, and native currency there is called Ether. So let's say it has 2 ETH, and let's say it wants to send 1 ETH to Carol and 1 ETH to Bob. And of course, Alice can just send 2 transactions, 1 ETH to Carol and 1 ETH to Bob. No big deal. But let us suppose Alice is like, how can I do it in 1 transaction? Is there a way? And what she can do is she can write a smart contract. Okay, so it's kind of a different entity which will live in a database of Ethereum, and it has the following code: if X, where X is any address, where X is any number, if X ETH received, the half of that is sent to Bob, and another half of that is sent to Carol. Okay, it's a very simple code. If I receive X money, send X divided by 2 to Carol, and send X divided by 2 to Bob. So this smart contract, this code, lives on Ethereum blockchain. And if Alice sends 2 ETH to the public key of this smart contract, I didn't write the public key here, I should have. So if Alice sends to a public key of this smart contract 2 ETH, well, the code gets executed, right? The state transition function gets executed. So 1 ETH goes to Carol and 1 ETH goes to Bob. And so with this example, you can realize that you can actually code up pretty much anything. You can code up a different currency, like a token, which lives on Ethereum. So a token is like another currency which is inside Ethereum. You can code up a database of a bank where people deposit money and withdraw money. You can cook up, like something like a multi-sig, where some people control a smart contract only if, for example, Alice, Artem, and Vartan send signatures, multi-signature wallet. You can cook up many things. And the point is that let's say last 6 years, from 2017 to 2023, this is what's going on in the space. Everyone, not everyone, but people try to come up with different applications. So these are usually called decentralized applications. Okay, I'll even write this. So the word is decentralized application, or sometimes they're called protocols on top of Ethereum. And there's many of those. There's prediction markets, there's decentralized exchanges, there's lending protocols. And to be honest with you, to be completely honest in a blunt way, nowadays Ethereum actually hosts a completely separate decentralized financial system. And we called it the DeFi, decentralized finance. And it secures about $100 billion of various activity. I mean, people, save money there. They get yield like, I don't know, 4% per year or something like that. people trade there, people take loans, for example. It's a separate financial economy there. And there's different smart contracts that are involved, which are decentralized exchanges, money markets, derivatives, many different super interesting things. And I'm happy to send links about those if you're interested. And the really mind-blowing property of those is that they function autonomously, okay? So in this smart contract, there's nobody who runs it, right? It's the nodes in the network of Ethereum who run the code. So whatever bank or decentralized exchange or whatever money market that you code up here, there's no owner of that. It's run autonomously, governed by code. And this is a truly a paradigm change, because some of you are in the US and some of you are in other countries, and you know that all the financial systems in all our countries, they run on the fact that there's different companies that have different responsibilities, and there's systems of checks and balances. Sometimes it doesn't work, sometimes it works, but there's a ton of fees that users pay to the systems, and some of those systems become kind of intermediaries that just rent the fees. Like, for example, the Visa networks, it's from 1% to 2% fee on every Visa purchase, which is, by the way, baked into the price. So whenever you buy something in the shop, and it says it's for free, you just swipe your card and your balance just decreased and you didn't pay any fees to anyone. This is not exactly the case. The fees are in the price of a product. They're hidden, okay? And this is a new system without those fees, without central points of failure. And this is, in my opinion, the kind of a revolution that is going on right now. And it's a revolution that separates money from state and separates kind of money services. So Bitcoin separates money from state. Ethereum separates money services from state. Yanis says, be very suspicious of anyone that tells you this is for free. There you go. Yeah, I agree with that. And I kind of wanted to, maybe a remark is that Ethereum is different from Bitcoin in many ways, but one of the ways is that the consensus mechanism there is different. It's called proof of stake. Super interesting stuff. I would enjoy covering that, but that will take another 1.5 hours. But it's an important remark. And then next, there were a couple of challenges into the future that I wanted to talk about, but I already took a lot of time from you. So I'll stop here. Thank you so much. And of course, if anyone has any questions, I'm happy to answer.
Well, I do. One question is, what about taxation? Because one incentive to invent money for the government is just to tax people by devaluating money and just controlling all these transactions. So how does a government how do you make them happy? Because you avoid all of it.
Yeah, that's a good question. It kind of pertains to the philosophy of what's going on. Well, let me address it in 2 ways, okay? So the first is the blunt answer. The blunt answer is there's no way to kind of embed taxation or embed something like that into the system, into the native currency of the system. So in that sense, it is a direct direct offense, direct threat to the government's power of control over money supply. And this is why, for example, the US government really doesn't like what's going on, doesn't like the space that much, and certain kind of organizations in the US government like SEC are cracking down hard nowadays on the space. But let me maybe give you a bit more nuanced answer as well. A more nuanced answer is that it is my belief that the systems will coexist for a while. What do I mean by this? Well, so you have to understand that this Ethereum new blockchain, it really is, it offers an alternative, not only money, and it does offer an alternative money in the form of Ether, but maybe more importantly, it offers alternatively an alternative money system. So right now, banks use the SWIFT protocol and some other databases to kind of manage what's going on with money supply and et cetera, et cetera. But Ethereum offers a better kind of rails for that, where there's going to be more transparency and more efficiency. So that's my first answer. That and the key kind of product, the key kind of buzzword that I need to tell you right now is that it is a stable coin. So stable coin is a token on top of Ethereum, which is pegged to $1. And there's many stable coins. The most famous ones are USDC and USDT. And essentially, this is the way to transmit dollars on Ethereum. So on Ethereum, you can send each other Ether, but you can also send each other dollars. And it's going to be way more efficient than if you do it on a Visa network, essentially. So that's kind of a more nuanced answer. And let me say that, yeah, the transition from kind of state money, dollars that we have right now, to separate money, Bitcoin, Ether, is a very long transition. It's not going to happen even in 10 years. It's a 100-year transition. However, the transition to a new money system, to decentralized finance, is a different story. And I think this decentralized finance that I'm describing to you makes sense to build with stable coins as well.
Mm-hmm.
And then, yeah, there's some messages in the chat. Yeah, the additional links. Okay, yeah, you know what? Additional links, I will maybe collect additional links and add them to slides. And then there's a link to slides, on the page of the talk. So I'll write this to myself. So I'll add those links to my slides at the end.
Yeah, so all the slides are uploaded, and this newer version will be uploaded to the researchseminars.org, where all our talk information is, so you can follow it too. And of course, you guys could just start talking to each other via email, and it's just one of the purposes of the seminar to make people, talking each other and knowing each other.
Yeah, feel free to email me at any time. This is my email. This is my Telegram handle, and I'm more than happy to answer any questions. But yeah, just to answer your other question, how is exchange between Ethers and dollars determined? Great question. It's supply and demand, right? Ether is a new native currency to Ethereum. BTC, Bitcoin, is a currency of Bitcoin. All those exchange rates are determined by supply and demand. On the centralized exchanges and decentralized exchanges.
Is there an economic basis for what one Ether corresponds to? Like maybe it corresponds, let's say, to spending 1 kilowatt hour, let's say.
Yeah, so that's a good question, and this kind of this goes to the idea that if you have money, it should correspond to something in the real world. And we had this model where money corresponds to gold, right? And then with Nixon, president of the United States, he essentially transitioned the system into the fractional reserve system, where only a fraction of dollar supply is reserved, corresponds to gold. Okay, and but still the idea is in the minds of people that money should somehow correspond to something. And with Bitcoin, someone could say, well, this money corresponds to the burned electricity that we have. Yes, you can think about it this way. But let me offer you kind of a more interesting idea, a more nuanced way of doing this. I don't think money has to be backed by anything, as long as there is consensus that it is money, and as long as the supply of this money is in control. So what do I mean by this? Consider Ethereum network. Right now, there's I don't remember exactly, about 80 millions of ethers, something like that, maybe 100 millions of ethers. And the point is that the rules with which ethers are issued on the Ethereum network are there. It's like a social consensus. It's written in code of those nodes, and it's written in such a way that there's not much inflation of Ethereum. It's less than 1% per year of inflation for Ether. Okay, so it's some kind of decision in the network how much is the issuance, and then maybe to even describe something else in more detail. Ethereum works in such a way that the fees that users pay in Ethereum are burned, so that there's Ether issued as a reward for block producing, and then there is Ether burned. And in fact, Ether burned is even more than Ether issued. So you could say that right now Ether is a deflationary currency. Its supply is constantly decreasing. So to answer directly your question, there's nothing hard in the real world that backs this, but there's a very developed ecosystem on top of Ethereum where everyone agreed to this particular issuance schedule, and that there's going to be not more than, let's say, 120 millions of Ethers. And this is what gives legitimacy to the supply dynamic of Ether. And then, of course, the demand is variable, right? The supply is there. I told you how it works. And now demand is another equation. How many people want to use Ethereum? Now, you use Ethereum to use the network. So if you want to run this smart contracts or decentralized finance, whatever, you need Ether. So that's why you want to buy Ether. That's where the demand comes from.
So do you think that we will get rid of this old bank system one day and we'll start just using all these things instead of what we have now?
I don't know. I mean, so let me give you kind of some things that I know. I know that this space, decentralized finance, is more efficient and it grows every year. I mean, it grows in bubbles, just as any new technology. Any new technology, grows in bubbles, but on average, it does grow because it is more efficient, more transparent, etc. It has many good properties. So as a consequence, I am convinced it will coexist with the current system. Okay, there will be our current system, centralized finance, or we call it traditional finance, TradFi. And there will be DeFi, decentralized finance, and we'll be able to go from one to another and from the other to the first one. So they will coexist. Now you're asking, okay, when decentralized finance will become big enough for every person on earth to rely on decentralized finance? Will we actually transition there? And the answer is, I don't know. And this actually speaks to Armen's question, because there's kind of important things that government controls, like money supply, I don't know, interventions in the emergencies, like crisis and things like this. And I don't know how it will play out, but I know for sure that the systems will coexist. And let me just maybe speak a little bit to this question that in order for decentralized finance to be as big as traditional finance, we need to solve the challenges. And the challenges that I had in mind are the scalability challenge and the privacy challenge. And the scalability challenge is that because the system is decentralized, it is not very efficient. It is not fast because you cannot demand all nodes to be very beefy and fast nodes. So there's this challenge of being fast. For example, Ethereum is about 17 transactions per second. It's not enough. So, but there are solutions like rollups and layer 2s for scalability. And then there's a privacy issue. You know, Vartan was always asking, but everyone can read everyone's usernames and balances. And yes, that is a problem. And there's solutions to that as well. But those are like deep research areas that there's kind of many faces of those questions, many approaches, et cetera, et cetera. Yeah, Armen, did you have another question?
No, all my questions are being answered. I'm happy with that.
Cool.
I think the scientific point of view is very interesting. Now we have our central banks and just relationship between countries. We borrow money from all these things, and if we just that's like what's going to happen when we just if we start using all this system and it's some kind of a new field to study.
Yeah,
a new field of economy.
I would say the key word here is the key, not the word, but like the key field is called Austrian economics. So there's a bunch of people who put out the idea that, hey, what if we do economics where the money supply is actually fixed, straight up fixed. We don't deflate dollars, we don't, just fixed. That's what's called Austrian economics. You can Google it. There's Hayes and a couple other people who studied it, and they actually came up with pretty good models. And the idea, the idea there, just to maybe give you a glimpse of that, is that there's not going to be huge bubbles. Like in our system, we have huge bubbles because people can borrow money from each other. And then, the government has to print a lot of money because it cannot unwind all the borrowers and because many banks and entities are default. So that's kind of how our systems work. We borrow many money from each other, and then the government just bails everyone out because we cannot unwind the system. And the idea behind Austrian economics is that basically we keep the system and we unwind it, and those who cannot, and those who suffer, they suffer, but we never kind of distribute the pain. And the end result is that the bubbles are shorter. So the people borrow, but then it's kind of quickly unwind. There's never kind of huge bubbles. And more importantly, the supply never inflates too much. The supply never inflates at all. And so therefore, there will never be like a bubble that we experienced just right now. For example, when the COVID started and the US printed more than $1 trillion amount of dollars, from 2020 to 2022, everything skyrocketed. And now we're paying the price. There's kind of inflation, and then to battle inflation, the government raised rates, and now the economy is not very sturdy. So we might slip into stagnation right now. So we're kind of paying this price of printing a lot of money. And the Austrian economics just says, hey, we don't have to pay the price. We can just keep the balances and keep each other accountable.
Yeah, on that point, Artem, that's actually very, that's the first time that I hear that Bitcoin is based on deflationary structure for money. Because actually we did have that structure with gold. Because gold, you need to mine it. Okay, so it takes now whether so the counter logic was like, why we're going to spend so much resources to dig up gold in order to bury it again in the vaults. So, but that conundrum of the gold standard, I think, is resolved with with Bitcoin and Ethereum. But I think that's not exactly true, because in order to mine Bitcoins, you need actually to spend much energy to solve this, like number theoretic elliptic equations to find the solution. And then what's the point of that? I mean, if it has an academic purpose, if you want to find the solution to a mathematical equation, but economically it makes no sense at all. And there is some ecological criticism to Bitcoin. But,
exactly.
But you said that Ethereum doesn't do that. How does Ethereum create its money supply? Because if we have a fixed, like, the problem with inflation is that when, let's say, it's a winner take all system. So if I manage for some reason, is because I'm smarter or because I'm more canny, and I can steal from everybody and then I can gather all the money, then that's no good for me, unless I can, like, because I have needs that I need to satisfy, which I cannot do by myself. So I need people to collaborate with. And then I will redistribute the money. Because I will say, Artem, here is some, $100, do this for me. And likewise, and that's how the economy is supposed to work. But when somebody manages to take all the money, and then the solution is, oh, we're going to put more money in the system, then I'm going to becoming more and more powerful. That's why these centralized governments are the creators of inequality, because they keep pumping money into a system which creates inequality. Because even with the slightest advantage, that was the point of my question with the fees. That even if you get a slight advantage, eventually, exponentially, you're going to dominate, and that's what we see actually it's happening with the economy. Advantage begets advantage, and inequality begets inequality, unless you do what you say. In other, you fix, you stop pouring oil into the fire, and then the system reorganizes itself.
Yes. Yeah. Thank you for the question. This gets to the heart of the problem. And the heart of the problem, as you described, maybe I'll just describe it in like one sentence. Basically, money begets power, and power begets changing the system in such a way that there's kind of more power flows into that. The money distorts the incentives. Okay, so that's kind of the punchline. That's why it's winner take most, because as you have a lot more power, a lot more money, you have a lot more power, and your incentives are not to help others. And the punchline about the Ethereum, and there's kind of two things. So the first thing is what's the punchline, and the second is how it works. The punchline is that the system cannot be rigged. So even though there are people with tons of Ethereum, Ether. There's people with less Ethereum. But the point is that they all play with the same rules, and they will never kind of hijack the system in such a way that advantages them. Even though they are incentivized, of course, people want more money, and if you get a taste of money, you want. And the reason is because in old world, in traditional finance, you have more money, you have more power. In Ethereum, you have more Ether, nothing comes with it. You just have more Ether. Okay, you can buy your yacht, you can maybe buy another house, but you cannot do much in Ethereum network with more Ether. There's nothing. So you earn, by the way, okay, and so that's the punchline. It's just the money, the number of Ethers doesn't do anything in Ethereum network in your advantage. Now, of course, the key question is, how does this work? How does the system work? And the system work, the keywords is a proof of stake, okay? And essentially, the idea is that all these nodes that are in Ethereum, they put up a stake, and the minimum stake is like 32 ETH. And they say, hey, this is my stake, and they lock it in a certain smart contract. And they say, I'm gonna validate the network, okay? I'm gonna, put blocks, validate balances, validate signatures. I'm gonna execute code inside Ethereum. I'm gonna do everything as an honest node. I'm gonna download the core Ethereum client. And if I don't, I will lose this Ether. So this is why it's called proof of stake. I stake my 32 ETH, I validate the network, I add blocks, and if I do anything malicious, I lose that Ether. So that's why the incentives are aligned. I am aligned to serve the network of Ethereum, because if I don't, my stake, my 32 ETH will be slashed, and well, ETH costs money, so I'll lose money. You might ask, well, why are you incentivized to validate? Like, what's good about it? Okay, you're not malicious because you will lose it. Why you validate? And this is because there's an issuance. There's 1%, or there's even less than 1% yearly issuance. So I get the reward. And for every validator right now, if I validate Ethereum network, I'll get 3% annual. But notice, if I have 1,000 of ethers, or if I have 32 ethers, it doesn't matter. I'll get 3% annual, and no, I'll exert no power over the network. So that's kind of, those are my answers.
And how does Ether get burned? You mentioned it can get burned. How and why?
Yeah, this kind of gets a little tricky, right? So I'm a node, I get the reward, and this comes from issuance. Now, why Ether gets burned? So this is the answer is the answer is because too many people want to input transactions into Ethereum. And because there's a congestion on the network, by the way, it's every second. In Ethereum, block happens every 12 seconds. So every 12 seconds, a lot more people want to put transactions into Ethereum than there is space. So there is a congestion. And in economics, when there's a public good that is highly demanded, right? What's a good way to resolve this friction, to resolve the mismatch of supply and demand? Well, you put an auction. So there's every 12 seconds, there is an auction for Ethereum block space, and certain people have to bid Ether for that. So if I want to include my transaction to Ethereum, I need to win an auction. So I need to bid with my Ether. And that bid, now the question is, okay, where does this bid go? I need to pay it to someone, right? I could pay it to a miner, or sorry, to the nodes, right? But the interesting thing is, well, then nodes, it's actually like it's not exactly nodes who own Ethereum network. The Ethereum network is owned by all the community, and you could argue that Ether, the token, is a good proxy. So it would make sense that this auction bid, where I bid, let's say, I bid 1 Ether to include this transaction to a block. Okay, where does this 1 Ether go? It makes sense to distribute it over everyone in Ethereum network. But distributing to everyone in Ethereum network is the same as burning, right? If you distribute something to every participant of a network, is the same concept as a burning currency. So burning Ether is a way to distribute fees that we pay to include our transactions into blocks to Ether holders. And you might ask, well, why Ether holders? Well, it's because it's the only proxy to Ethereum network. There's no other mathematical, like I cannot distribute Ether among I don't know, users of Ethereum, because how do I identify the user? But I can distribute it among token Ether holders. I just burn Ether. So that's the interesting kind of dynamic there. And you, well, you know, for those who are in, sorry, not RIP, but EIP 1559, you can Google that. This is the kind of the new fee model where the burning was invented. So Google that, and there's many, many more details on top of it. But it so happens that the burning, the deflation pressure right now is bigger than inflation pressure. So effectively, the currency becomes deflation. And you can view this in terms of profitability. The network pays nodes to do the service, and users pay network for the services. And the fact that Ether is deflationary just it is just another way of saying that the Ethereum is profitable. People want to pay more to Ethereum than Ethereum pays nodes to validate the network. Any other questions, comments?
Okay, I think there are no more questions. So,
all right.
Yeah, thank you, Artem. It was really very interesting and I think useful.
Yeah, it was a pleasure. Thank you so much for listening.
Yeah, thank